Hello, so this is the first video that you'll be watching in the non-parametric statistic video portion of the class. When you're done with this video, go and take the self-quiz and be prepared for questions on chi-square analysis to be showing up on your first exam. So what we're working in is a category of statistics called non-parametric. And in class, we've focused primarily on this category on the right, and we're going to focus there in all of our lectures, where the dependent variables will have normal distributions, they'll have fairly decent sample sizes, and you'll have at least interval or ratio dependent variables. Now, sometimes we have data that really just doesn't meet those basic assumptions. Sometimes the dependent variables are not normal. Sometimes we don't have large sample sizes very often in thesis and dissertation data, and sometimes we have dependent variables that aren't interval or ratio level of measurement. And any sort of combination of one of those three things, usually a non-parametric statistic is preferred. It's not, you'll see it's not always done in the data. In real study or in published data, often people are more likely to do parametrics than non-parametrics. But you should know about it. It is best practices in statistics. So a chi-square test is the first one we're going to cover because it really more lines up with our descriptive statistics lecture, but I wanted to make sure we taught the process of inferential statistics testing. So they're most commonly used in survey research designs, which is your most descriptive form of research design. And here we're going to introduce primarily, we're going to start with a one-way chi-square, but they determine if differences exist in the frequency of a response to one or more nominal or ordinal variables. So the key word there is frequency, and we're going to keep coming back to that. Also, a chi-square statistic measures whether or not a relationship of frequencies between two or more nominal or ordinal variables exist. This is the only time you're going to hear me use the word relationship outside of correlation. But when we talk about relationship here, again, notice that it's the relationship of frequencies, and so that's a key component. Therefore, chi-square is considered non-parametric because our dependent variables are always going to be nominal or ordinal. There is no non-parametric equivalent of chi-square. You'll see throughout the semester most of the non-parametrics I'll introduce to you are equivalents of a parametric statistic, but there is no parametric equivalent for this. Now, there's two forms of chi-square, a one-way and a two-way. A one-way chi-square compares frequencies across one nominal variable or ordinal variable, ideally with less than 4 levels. So that would be something like division 1, 2, and 3 would be the 4 levels. NCAA division would be the variable. Question might be, does a pattern exist to the response of participants to a particular survey question? Are there significantly more yeses than nos? Are there significantly more females or males that responded to a survey? A two-way chi-square tests to determine if two nominal variables or ordinal variables are related to one another, specifically related to frequency. So don't overuse this word relationship because that's going to shout correlation to you later this semester. This is also said to be the independence of two nominal variables. So a question like this would be, do males and females, gender being the first nominal variable, have similar preference for fast food chains? Let's say we're comparing McDonald's and Burger King, a second nominal variable. So a one-way chi-square only has one variable. It doesn't even really truly have an independent or dependent variable. It's just looking to see, is the expected frequency, and the frequency can be measured either in an n, a count, or it can be measured in a percentage. Is the expected the observed frequency, the observed equal to the expected? Now let's define those two terms. An expected frequency is, usually goes off normal probability. So if I had a sample size of 413, we expect an even breakdown between these three categories. Therefore, the even breakdown is 137.7 per category. Clearly, you can see that many, many more people identified in this, we have a much higher frequency than we expected in this category, and much lower frequencies in the slightly agree, slightly disagree, and the strongly disagree, disagree category. So that's saying that the observed frequency, how people answer the question, is different from the expected frequency, what we go based on normal probability. Now, expected frequency can also, it doesn't necessarily have to be normal probability. It could also be normative numbers that you can get from other data. For instance, if I were to do a survey based on the strength and conditioning coaches, and I used the National Strength and Conditioning Association data set, well, they have data that says that their membership is 70% male and 30% female. So my expected percentage or frequency of males would be 70%. My expected frequency of females would be 30%. So I could actually enter into this expected N in SPSS and alter it not to be normal probability, but the default is normal probability. So here we see that because of this high unexpected frequency here, high observed frequency, we do have a very high chi-square value. The chi-square value is compared to a chi-square distribution. The chi-square distribution, then we see that we fall into the chi-square distribution looks like this, and we fall into the rejection range, or the critical range, saying that p is less than 0.05, and we'll say that there are significant differences do exist between the responses. Unfortunately, I have a typo here because they are not expected to equally agree, so I have to fix this. There was a significant difference found in the observed and the expected frequencies, the extent to which employees agree they're motivated to do their job. Obviously, p was less than 0.05 because chi-square was so big. So instead of no significant difference, that should say a significant difference was found. And then I deem that employees were more likely to be motivated. And then we have what is a correct outcome, which is employees are expected to report higher frequency of being in agreement, to which they agree or they are motivated to do their job, than disagree or moderately kind of neutral response. A two-way chi-square has two variables into account. So a two-way chi-square, in this case, where you're looking at, we're using I'm overworked as one variable. That's the sentence. And then we're seeing if males or females are more likely to strongly agree, slightly agree, kind of have that neutral response, or the strongly disagree response. And so again, here you can see that there's both counts and percentages in each one of these cells. And what we're looking to see is the percentage or the count different from what we'd expect? So is the observed different from the expected? If you can see, overall these numbers are fairly split evenly. They look pretty normal for males and females. So not surprisingly, we would go down and we'd use this first line here, this Pearson chi-square. And we'd see a chi-square value of 0.914. That's relatively a very low number. That would fall in the non-critical region, and so our p-value is above 0.05, suggesting no differences exist, or no relationship of frequencies exist between the two variables. Then I go into my next one. No significant difference was found in males and females in the extent to which employees would agree that they are overworked. A nice low chi-square. The degrees of freedom are reported there. P is greater than 0.05. And males and females are expected to report similar frequencies when describing the extent to which they agree they are overworked. So, noting an important thing with significant difference, if the p-value is less than 0.05, then a difference does exist in the observed frequency across the cells. To generally figure out where those differences exist, later this semester we'll be doing what's called post-hoc analysis. For chi-square, though, it's pretty straightforward. If you see an 8 to 12% difference in the cells, then that's going to really jump out and say this is where the significance difference exists. So that kind of highlights that between, if we saw 8 to 10% difference between males and females on the slightly agree, that would identify where that difference exists. A significant chi-square, just to give you a visual, this now looks at, I feel this program offers me adequate job security, and it compares part-time and full-time employees. And you can see now those 8 to 10% differences exist here, they exist down here, jumping out to us. It's not quite 8 to 10, in the neutral, that's not quite 8% yet. It's close, but it's not quite. But we do see a significant outcome. When we look at our Pearson chi-square, we have a Pearson value, or chi-square value, with a p-value less than 0.05. So we identify that a significant difference does exist, and we'd say that full-time employees were more likely to agree that they have job security, and part-time employees would be more likely to disagree that they have job security. which is essentially what I have written here. Full-time employees were significantly more likely to agree or strongly agree that their program offers them job security when compared to part-time employees. And then a layman's terms version for the conclusion statement. Full-time employees are more likely to report that they agree that their program offers them job security than part-time employees. Alright, so you finished video 1. Now I want you to go take the self-quiz. Please bring any questions you have on this video to class. Thank you very much.